Hello, and welcome to my presentation. Today I'll be discussing derivation, the history, its applications, and most importantly, how to do it. The concept of derivation has been around since the ancient Greeks, when Archimedes developed a method for calculating the area of a circle using geometric principles. Although this wasn't developed at the time, his process involved the concept of derivation. It was over 2,000 years later, in the 18th century, when Gottfried Leibniz and Isaac Newton independently developed the concept of the derivative and modern calculus in the form we see today. Simply put, the derivative of a function is the study of how a function changes as its input values change, and has many applications in fields such as physics. You know how far the car drove in 10 seconds? How would you find out its velocity? Derivation. You work in medicine. How do you calculate the rate of absorption, distribution, and elimination of drugs in the body? Derivation. You're an economist, and you need to know the marginal costs of a production. Derivation. So how do we do it? Let's start by looking at it in its simplest form. Here we see Leibniz's notation for differentiation, the process of getting the derivative, along with Newton's down at the bottom. Here, delta, the triangle shape, denotes a change in. So we have a change in y over a change in x, sometimes referred to as the rise over the run. So if we think about a graph that shows distance over time with a constant rate of change, to calculate average velocity, we would take two arbitrary points on the graph, A and B. Then we find the difference between the x-coordinates and the y-coordinates, so we're subtracting A's x-coordinate from B's, and we do the same here for y. Once we've done this, we then divide them. So if we have distance in miles and time in hours, we end up with miles per hour. Now things get a little bit trickier when the rate of change or slope of the line is constantly changing. Here's an analogy to explain how we get to the standard notation of how to calculate this. When you stand on the beach and look at the horizon, it's straight. Yet astronauts have taken pictures of the Earth that show it's round. The reason for it being straight is that we're stood on the surface. We're dramatically closer to the horizon than the astronaut, hence how we see it as a straight line. This is fundamentally what we do in scenarios where the rate of change constantly changes. We take the point we're interested in and move the smallest possible point over and calculate the difference. The closer those 2 points are, the straighter the line between them is, and the more accurate our calculation is. The general notation can be seen at the bottom. Here we have our x value, and h is the second point we take to differentiate, so we're calculating the derivative as h approaches 0. Now when you know the function of your graph, there are some general rules that can help simplify the process. If the function of the graph is a constant, the derivative is 0. If the function is a line, like x, the derivative is 1. Now we come to the sum rule. This simply means if we have two functions added together, the result of this is that we take the derivatives of each of the functions and we add them together. The power rule is used when the function has an exponent, for example, x squared. So the derivative of the function, as we can see on the left, is calculated by copying the power in front of x and taking 1 from the exponent. So in this example, x squared becomes 2x to the power of 1, or 2x. If we have a constant in front of the function, then we must multiply the derivative by the constant. So to elaborate on the previous example, if the function was 2x squared, we would use the power rule as normal to get 2x, then multiply by the constant to produce 4x. Next we have the product rule. The product rule is used when we need to calculate the derivative of two functions multiplied together. To do this, we need to calculate the derivatives of each function separately, and then we do the left function's derivative times the right function, plus the right function's derivative times the left function. An easy way to remember this is left d times right, plus right d times left. We then come to the quotient rule. This is similar to the product rule with some slight differences. Similarly, you'll calculate left d times right and right d times left. However, you'll subtract the first from the second. And the other difference here is that you divide this equation by the function that is the denominator squared. And finally, we now come to higher order derivatives. Higher order derivatives are when you take the derivative of a derivative. So if we have the function f of x equals 3x squared, and we take the derivative of 6x, to get the second derivative, noted as f prime prime, we take the derivative of 6x, which is 6. We can continually do this to get the third, fourth, and so on derivatives. If we come back to the example of calculating velocity, the first derivative of a point on our distance over time graph would give us the velocity. Now if we take the second derivative, we can find out acceleration. The first differential gives us the rate at which the distance is changing in respect to time. The second differential gives us the rate at which the velocity is changing. We can then look at the second derivative, and if it's positive, it's accelerating, and if it's negative, it's decelerating. This concludes my presentation on derivation. I hope you found it useful.